Chang'e 4 sits motionless on the moon's far side, its radiation detector clicking steadily in the silence. The numbers streaming back to Earth tell a stark story. Cosmic rays bombard the lunar surface at rates 200 times higher than anything measured on our planet. Meanwhile, during its deep space trajectory that reached 57,000 miles from Earth, the Artemis 1 capsule collected data from beyond the magnetosphere. Inside, two female mannequins named Helga and Zohar bristle with over 10,000 radiation sensors. The data they collect reveals astronauts face radiation levels that dwarf anything experienced aboard the International Space Station. This isn't just about distance from home. Something fundamental shifts when humans step beyond Earth's immediate neighborhood. The cosmic ray environment that barely registers in our daily lives transforms into a relentless bombardment that could end careers in months rather than years. NASA's universal career radiation limit of 600 millisieverts means a 25-year-old astronaut could spend approximately 1 year conducting surface operations on the Moon before hitting their lifetime exposure cap. The August 1972 solar storm, which erupted between Apollo 16 and 17, could have delivered doses approaching acute radiation syndrome to any lunar explorers caught outside their shelter. What transforms the relatively benign radiation environment of low Earth orbit into this cosmic shooting gallery? The answer lies in Earth's invisible armor and what happens when astronauts venture beyond its protection. Earth's magnetosphere extends tens of Earth radii outward, creating a vast cavity in the solar wind that deflects most charged particles streaming from the sun and deep space. This magnetic bubble represents the difference between life and sterility. Inside this protective zone, natural background radiation averages just 1 millisievert per year across the United States. Step outside, and that gentle shower becomes a torrential downpour. The International Space Station, orbiting at 400 kilometers altitude, still enjoys large protection from this magnetic shield. Astronauts there accumulate roughly 50 millisieverts annually, already 50 times higher than ground level but still moderated compared to deep space. The Van Allen radiation belts, two donut-shaped zones of trapped particles, create an additional barrier between 1.1 and 7 Earth radii from the planet's center. James Van Allen's original analyses showed that lunar missions could pass quickly through weaker regions of these belts, limiting exposure during transit. But beyond the magnetosphere's edge, this protection vanishes completely. The geomagnetic field imposes what scientists call a rigidity cutoff. Particles below 15 billion electron volts at the magnetic equator simply cannot penetrate to low Earth orbit altitudes. Remove that barrier, and astronauts face the full spectrum of galactic cosmic rays and solar energetic particles. The 1859 Carrington event demonstrates the scale of possible solar storms. Telegraph fires erupted across the globe as auroras appeared as far south as the Caribbean. That coronal mass ejection reached Earth in approximately 18 hours, generating induced currents powerful enough to electrify metal infrastructure worldwide. Modern analysis suggests unshielded astronauts caught in a similar storm beyond Earth's magnetosphere could receive multi-gray radiation doses well into acute radiation syndrome territory. ESA's SMILE mission will soon image the magnetosphere directly in X-rays, revealing how this invisible shield flexes and fails during space weather events. These observations will refine models of when and how Earth's protection breaks down, critical data for planning missions beyond its reach. Void, beyond Earth's magnetic embrace lies a cosmic shooting gallery that never stops firing. Galactic cosmic rays span energies from 1 million to 1 billion trillion electron volts, a range so vast it defies easy comprehension. 85% are protons, 14% helium nuclei, and just 1% heavy ions. But that tiny fraction of heavy ions contributes disproportionate biological damage. These rare heavy nuclei, elements like carbon, oxygen, and iron accelerated to near light speed, deposit energy in dense clusters along their paths through tissue. Linear energy transfer measures this concentrated damage, where X-rays scatter their energy diffusely. Heavy ions create narrow tracks of devastation that overwhelm DNA repair mechanisms. The solar cycle creates a counterintuitive trade-off that mission planners must navigate carefully. During solar maximum, the enhanced solar wind and tangled magnetic fields reduce galactic cosmic ray background by up to a factor of 2. But this apparent benefit comes with a dangerous catch. Solar maximum also increases the probability of major solar particle events, those rare storms that can transform manageable chronic exposure into acute medical emergencies. Chang'e 4's lunar lander neutron and dosimetry instrument has been measuring this environment continuously since landing on the Moon's far side in 2018. The German-built detector stack records equivalent dose rates of about 60 microsieverts per hour at the lunar surface. That translates to roughly 1.4 millisieverts per day for an unshielded astronaut, 5 to 10 times higher than transatlantic flights and 200 times Earth's cosmic ray background. Artemis 1's 25-day mission provided complementary data from deep space itself. The Orion capsule carried Helga and Zohar, two female torsos outfitted with passive detectors and active sensors throughout their synthetic bodies. Analysis revealed a 4-fold dose variation inside the capsule depending on location and shielding geometry. Most surprisingly, a 90-degree spacecraft orientation change during Van Allen belt passage reduced cabin dose rates by 50%. This finding offers mission planners a powerful operational tool that costs no additional mass. The August 1972 solar storm remains the canonical worst-case scenario for lunar exploration. Erupting between Apollo 16 and 17 missions, this event delivered particle fluxes that could have produced severe radiation sickness in unshielded astronauts. Computer models using the Brin-Turn transport code suggest organ doses approaching the thresholds for acute radiation syndrome were possible during this storm's peak intensity. NASA's Space Radiation Laboratory at Brookhaven National Laboratory recreates this hostile environment using ion beams from hydrogen to bismuth at space-relevant energies. Researchers can simulate the exact energy spectra and particle types astronauts encounter, testing both biological responses and electronic systems under controlled conditions. Understanding what this radiation does to human tissue requires diving into the molecular battlefield inside our cells. When cosmic rays strike DNA, they don't just create simple breaks that cells can easily repair. High-energy heavy ions generate clustered damage sites where multiple breaks occur within a single helical turn of the double helix. Linear energy transfer quantifies this concentrated destruction. Heavy ions at cosmic ray energies deposit 10 to 100 times more energy per micrometer than medical X-rays. This dense ionization creates complex DNA lesions that overwhelm normal repair pathways, leading to chromosomal aberrations and mutations that persist long after the initial damage. NASA's radiation quality factors weight physical dose by biological effectiveness. Iron ions at galactic cosmic ray energies receive quality factors significantly higher than protons, reflecting their enhanced capacity to cause cancer and other long-term health effects. This explains why heavy ions, comprising only 1% of the cosmic ray flux, can contribute a biologically weighted dose competitive with far more numerous protons. Mouse studies at the Space Radiation Laboratory revealed the stark difference between space radiation and terrestrial exposures. Carbon and silicon ions induce malignant transformation 7 times more efficiently than X-rays at equal absorbed doses. These experiments use the same ion species and energy ranges astronauts encounter in deep space, providing direct evidence of enhanced cancer risk. The bystander effect adds another layer of complexity to space radiation biology. When researchers expose only 5% of cell nuclei to alpha particles, neighboring uniradiated cells still develop 57 mutations per 100,000 survivors. Compare this to 98 mutations when all cells receive direct hits, and the nonlinear nature of radiation damage becomes clear. At the very low particle fluences expected during deep space missions, many tissue cells may never experience direct traversal by heavy ions. Yet these cells still receive stress signals from irradiated neighbors through gap junctions and secreted factors like reactive oxygen species. This bystander communication means current risk models based on direct hits may underestimate the biological impact of chronic low-dose heavy ion exposure. Multi-omics analysis of 59 astronauts has identified mitochondrial stress as a consistent spaceflight phenotype. Altered oxidative phosphorylation, reduced antioxidant defenses, and disrupted lipid metabolism appear across multiple studies of both human crews and laboratory animals. These cellular power plants, already vulnerable to oxidative damage, face additional assault from high-energy cosmic ray tracks. Spaceflight-associated neuroocular syndrome may represent one visible manifestation of this mitochondrial damage. The condition, characterized by optic disc swelling and vision changes, affects roughly 70% of long-duration astronauts. While traditionally attributed to fluid shifts in microgravity, emerging evidence suggests radiation-induced mitochondrial dysfunction in eye tissues may contribute to retinal and optic nerve pathology. The specter of acute radiation syndrome looms over every deep space mission. This condition, triggered when the body receives large radiation doses over short periods, progresses through distinct clinical phases that could prove fatal without immediate medical intervention unavailable in space. Hematopoietic syndrome dominates the dose range from 0.7 to 10 grays, attacking bone marrow and blood cell production. Gastrointestinal syndrome emerges between 6 and 30 grays, causing severe vomiting and electrolyte imbalance. Above 30 grays, neurovascular syndrome brings rapid neurological deterioration and death within days. Large solar particle events represent the primary acute threat to deep space explorers. These storms, triggered by solar flares and coronal mass ejections, can deliver high fluences of energetic protons over hours to days. Analysis using sophisticated transport codes shows that unshielded astronauts could receive organ doses approaching acute radiation syndrome thresholds during major historical events. NASA's universal 600 millisievert career limit, implemented in 2017, replaced earlier age and sex-specific standards and further constrained astronaut radiation budgets. This conservative approach reflects growing understanding of cosmic ray cancer risks, particularly from heavy ion exposures that have no terrestrial equivalent. Artemis II, scheduled to launch during Solar Cycle 25's active phase, will face this exact trade-off between chronic cosmic ray exposure and acute solar storm risk. The mission will carry advanced biological experiments and radiation sensors to study real-time biological responses to the deep space environment. These investigations will provide important data for longer missions to Mars, where transit times of 6 to 9 months each way multiply cumulative exposure. Orion's radiation shielding analysis demonstrates how careful mission design can mitigate some risks without adding mass. Trajectory optimization and attitude control during Van Allen belt passages can halve trapped particle doses. Solar storm shelters, created by repositioning crew quarters behind the service module's bulk, provide additional protection during particle events. Space weather forecasting now offers real-time solar monitoring through multiple satellite networks. Ground-based observers track coronal mass ejections from eruption through interplanetary transit, providing hours to days of warning before particle arrival. This early warning system allows crews to take shelter and postpone extravehicular activities during the most dangerous periods. Yet fundamental questions remain about optimal protection strategies for Mars missions. The radiation environment beyond Earth represents a hard limit on human exploration duration without major technological advances. Current shielding approaches based on aluminum and polyethylene provide modest protection against galactic cosmic rays while potentially worsening exposure to secondary particles generated by nuclear fragmentation. The 300-fold multiplication factor that makes cosmic rays so dangerous to astronauts represents the complete loss of Earth's layered protection system. Our planet's thick atmosphere stops most cosmic ray primaries, converting them into harmless secondary cascades before they reach the surface. The global magnetic field deflects charged particles below 15 billion electron volts, excluding the majority of solar wind and lower-energy cosmic rays from near-Earth space. Chang'e 4's measurements prove the lunar surface delivers 1.4 millisieverts daily, what Earth gives you in an entire year compressed into just 8 months of exposure. Every deep space mission becomes a race against radiation accumulation, with career limits now capping total lunar surface time at roughly 2 years across an astronaut's entire career. The August 1972 near miss between Apollo missions demonstrates how solar storms could transform manageable chronic exposure into acute medical emergencies lasting days. Future Mars explorers will face this same cosmic shooting gallery for journey times measured in years rather than weeks, with no possibility of emergency return if radiation sickness develops. As humanity prepares for the next giant leap to Mars, the radiation challenge scales from months to years of continuous exposure. The invisible armor protecting life on Earth becomes starkly visible only when we step outside its embrace. Beyond that protective bubble, the cosmos reveals its true nature as a place fundamentally hostile to unshielded life. The cosmic rays that barely register in our earthbound existence transform into an implacable adversary that never stops firing. Each mission beyond Earth's magnetosphere writes another chapter in our understanding of what it truly means to become a spacefaring species. The price of cosmic citizenship, it turns out, is measured in millisieverts and counted in days.